Can you do the, can you do the light? Okay, so, here's how this kind of works. Paper, if I have any. Yay! All right. So let's say I had, what was that? Oh shit! All right. You guys have that sheet from yesterday with the chi-square problem on it. Yeah. Some of you guys probably need this sheet. It's the one that's got side 1 and side 2, and side 2 says goodness of fit at the top. That's the one where we did the incomes on the one side. Remember that? Yes. Incomes by state with the bachelor's degrees. You have no idea what I'm talking about. Probably need this. So it's this one. One side said this, and side 2 is this. Let's see if we can recapture this guy. So this problem, alpha is 0.05, right? And the whole idea with this is 0 would mean no difference between what I expect to happen. So if I have a bunch of M&Ms, I expect none of the colors to show up more than the others. And then we actually get a bag and we dump it out. We count how many there are before we eat them all. So if these were exactly the same, the calculation would come out to 0. Because this calculation captures the relative difference between what I see and what I expect. That's the basic idea of that chi-square formula. Right? What's the z-score formula tell you? The relative distance between the data point and the mean. In this case, relative related to the standard deviation size. Oh, shit. How are we doing? This is a nice analogy, yes?
What if the expected decimal is the total categories?
Yeah, so this here, right? Is that what you're saying?
No, like.
Oh! Yeah, then you just put that down. And because you, all right, so if I was talking about one family, and you're like, I expect there to be 3.5 kids there, yeah, here's something wrong with you. This is always talking about an average. So if I had several bags, I would expect an average of 7 across the board color-wise, right? So expected amount, expected always references in the long run. So yeah, it could be decimal. If I had 100, what was it? Oh, I don't remember. How many stupid? 42, there it is, Jeff. Right, if I had 40 M&Ms instead, 40 divided by 6 ain't nothing pretty, so you would just put that number down. I love it. Expected doesn't have to be an actual whole number, right? Doesn't mean I expect my M&Ms to come out all crumbled. I'm like, oh, that's about a quarter of an M&M. No. We talked yesterday about this formula and how it kind of makes sense, hopefully. It's very similar to how we had to construct the standard deviation. We had a square, because sometimes they're negative or positive. We want them all to be positive. We don't square root at the end just because that's sort of the way the distribution is built. I told you it was based on that folding thing, so that idea of everything being squared is built in, so you don't square root at the end. That's going to be one of the hardest things for you guys, because a freaking symbol has a square in it, but that's part of the symbol. It is the chi-square distribution. All right. If you were here yesterday, hopefully you're kind of with me. If you weren't, you better watch that freaking video. 0 would mean, if I do this work, the only way to get 0 is if everything's exactly the same. So that would definitely not be evidence that they were different, right? I like it. And you can't prove they're the same, but it would certainly not be evidence they're different. So really, the whole idea is, not only does it have to not be 0 to be evidence that they're different, but it has to not be 0 enough. It has to be far enough away, because it's just a frickin' sample. We only took 42 M&Ms, so it's got to be pretty far away. It's got to be this far away. So let's see, how the hell did we get that? Right? There's the one we calculated from the table. That's the amount we calculated. That's the relative distance that we are away from what we expected. That doesn't seem very far away, and sure enough, it isn't. So where the shit is that 11.071? Here's the first thing you have to get over with these. What would you think the degrees of freedom would be?
41.
And you would be wrong. The degrees of freedom, and that was so evil of me, I set you up for that, sorry. And there's no reason you should expect it to be anything different. Here, it's based on number of categories. Because that's actually what governs the shape of the distribution, is the number. Remember, if I only had 2, it looks really weird. It looks like that. Well, for you guys, like this. I showed you yesterday on the board. So the degrees of freedom is related to the number of categories that you have. So it's how many categories do I have? -1. And in this case, we don't use the letter N, because N would be 42. We use the letter K because it, start the word with a K and it still means categories. So K -1. So this would be 6 minus 1. The degrees of freedom is 5. That's the degrees of freedom. So in this number 2 problem that we're going to do, how many categories? 4. So then degrees of freedom would be 3. Okay. I like it. Not the number of people I talk to, but the number of categories they could fall into. I like it. Okay, so how do we get this? Well, these kind of goodness of fit tests will always be a one-tailed test. It's not really how the chart's set up anyway, but it's got to be far enough away. So tell me, where would 0.05 be out there? So if they are the same, if they really are the same, I would expect the bulk of the samples to show up here. There would only be 5% of the samples that would... Samples, Jeff? 5% of the samples would show up out there. So if they do get a sample randomly that shows up out here, that's evidence that they're not the same. Because they're so freaking far away from where they should be, right? So if M&Ms did follow this pattern, shouldn't most of the bags of M&Ms be close to that pattern then, right? So shouldn't most of it be close to 0? Well, what's close to me? What's far enough away? This number that we're about to get. And it's going to be the one that's only got 5% beyond it. That's why if I got a sample out there, holy shit, there was only a 5% chance of that happening, then more than likely it doesn't follow that pattern. This should feel and sound very familiar. I'm not going to make you do all the steps. It's very cut and dry and to the point, but I want you to be familiar with the idea of chi-square, where it comes from, and at least one use of it. So here's how we do this. Where's that 5%? It's to the right. I love it, yes. To the right. So look at how this is set up. Area to the right. I want 0.05 to the right. You guys with me? Everybody has this chart, or else I don't know why you're not raising your hand or doing something. So everybody's got this chart. And then I go down and I stop where? There. There's 11.071. That's where I got 11.071 from. Hey. All right. So it's got to be this far away, at least that far away, to show evidence that it's not the same. This here means the same. So really far away from there would mean not the same. On that level, please let that make all the sense in the world. So did we make it far enough away? No, we're like right there. We're at 3.143. So we have not found evidence to say that they don't do this. I know the double negative, but you're not in English classes, okay? You calm the shit down a little better than double negative. Yes?
How would you use the other side of the chi-square chart? Like
That would be the other formula I showed you. Right? And actually, let's do this number 2, and then I actually wanted to show you a little bit about what else you could do with chi-square, just very quickly, because you don't have to worry about it for the final. But I will show you one more thing you could do with it, and then you worry about 2 things. It would be confidence intervals that we would do. Yeah. How we all feel about number 1? Is that... What?
Remember like when we were doing the distributions, it was L1 times L2, and then it was L1 times L3?
Yes.
Is there something like that on these, or you just have to actually manually do it?
No, yeah, you could do the same thing. You could do L1 observed, L2 expected. This would be L1 minus L2, the whole thing squared. This would be L1 minus L2 squared. And this would be like L3. This would be L3 divided by L2, right? Totally you could do that. Yeah? Yes? Say again? What would negative? Nothing can be negative here.
So,
What's the smallest chi-square could be?
or just be zero.
Zero.
Like if it's square root.
And why does it make physical sense here? Zero would mean no difference. What would negative mean, right? It's like, were they different at all? You're negative. No, they were 2 off from each other, 3 off from each. You can't say they were negative off from each other. One of them's in this dimension. Yes.
Can you just explain like the claim? Because it said we don't have enough evidence to reject the claim.
We want to test to see if the colors are uniformly distributed. That's our claim.
Okay. We don't have to-
So, if they were perfectly always uniformly, this would always all be 7s.
Okay.
They're not. They're different. Are they very different? No, they're not different enough. So we did not find evidence, because that means they're exactly the same. Anything outside of here means that's evidence they're not the same. Anything in here is not enough evidence. So where we end up, not enough evidence.
Okay, from the formula above.
Yes. So that's like our Z star. Same idea as the Z star, and this is like our rejection region. Same exact idea.
Okay.
So we didn't make it, so we failed to reject. You don't have to be so formal in your wording on this one, though. But if you feel more comfortable, you can. Okay. I love you guys.
Then if it did, it would say you have enough evidence to support the claim.
You would never support the claim that they're equal. It's just, so right here, we did not find evidence to reject it. If we did make it, if our chi-square from this thing would have been 15, then we say we found evidence to say that it's not uniformly distributed. All right? And then we can go deeper and say, well, which M&M do they make more of? Is that because that color is cheaper to make? Who knows? Right? I'm not, like shit on M&M's. Yes?
Are we always going to have the LOS right there?
What's LOS mean? Level of significance. I've used that phrase a few times, but that's alpha. Alpha is the level of significance, because if I make alpha smaller, passing that test would be more significant. That means that my sample was even further away. So that's why we call that the level of significance. So if I made it 0.01 and I rejected it, that would be pretty significant. That would be, whoa, you passed the 0.01 test. That's hard. So that's why we call that level of significance. You guys look so excited. So let's do number 2, and then I'll give you this little worksheet. Let's do this one together, because it's the other way you can do things. Now, real quick, which one of these is going to be the easier one to fill in? No. Observed will always be. Why? Because I'm just going to tell you what the shit there was. So, how many had a level below 130? 120. Put a 120 there. All right, let's do that first. Observed is always the easiest, because you just write down the numbers they give. And the rest have. Ooh, you gotta like that. I did make it more interesting. 1, 3, 4, 60, so only 40 up here, it looks like. You guys see how I got that last one? 500 people. I tell you the first 3, the rest have a level, oh shit, so it's gotta be whatever's left over from 500. Okay. Now, what about, how many would you expect to have less than 130? How would you figure out, what's the pattern that we're seeing, that we're testing? We're testing to see if they follow that pattern. Well, what percentage of people do I expect below 130? 20%. So 20% of what? 500? Okay, now Phil leaves it. So the whole idea of this, we go to the secluded area, we observe cholesterol levels, and then we're going to check it against the general population cholesterol level distribution. We're going to see if there's a big difference, then we want to look at their diet. We want to look at what's in the water. We want to look at, is there radiation? Is there, I don't know. Right. Are they X-Men? I don't know. So, what's your superpower? Low cholesterol. Holy shit. 20% of 500 is 100. 30% of 500 is 150. 35% of 500. One who? And then 15% of 500. 75. And then a quick check is these better added to be 500, right? Okay. You don't have to, that's a check. So make sure you didn't do something freaky with the percentages. You don't want to create people out of nothing. That would be freaky. So the actual work entailed here is not difficult. If you want to, I can show you. Oh, does anybody need a calculator? I can show you how to do it in the calculator. Oh shit. Do I have my calculator? Yes, I do. It's right there, John. Yes. All right. Let's show you how you do this with the calculator. Clear, Jeff. There you go, buddy. So I got 20, 40, 100, bless you, bless you. 150, 175, 75, and then L3 has got to be parentheses L1 minus L2 squared. Everybody cool with that? You guys see that? You don't have to. I'm never going to give you like 78 categories or something, so you don't really have to do it in a calculator like this.
Can you do that one more time? I messed
Yeah.
up.
All right, here we go. You got L1, L2? Then you go up to L3, and what's it supposed to be? Observed, that's in L1. So, parentheses, observed is L1, minus expected is in L2, squared. Observed L1 minus expected L2 squared.
Mine is kind of like this big
And you put parentheses.
Yeah. Oh, I put 100.
Oh, you put 10 in there. Oh, neat. Okay. Alright. And what I want L4 to be, L3 divided by L2. So make sure you can get those numbers. And again, you don't have to use the lists to do it like that. You could do each one individually. There's not going to be that many. So that last column represents the relative difference between what I saw and what I expected. That's why I love this test so much. It's deceptively simple. It's crazy simple. It's almost too simple to believe it tells you anything. So you fill in all this shit. Let's see. 400, maybe 100. I'll tell you what, if I ever get my eyesight back, I feel like I'm superhuman. Alright, so let's sum up L4. I'm just going to do it fast, whatever the hell way you want to do it. The sum of L4 is 106.476, it looks like. So make sure you can get all of that. Let me know if you have any trouble with any of that. Yes, sir.
Would you put right here again for L2?
L4 has to be, if you look at it right here, sir, has to be this. So that's in L3. So it's going to be L3 divided by E, which is in L2. Bam.
Liar.
I mean, and just looking at it, just looking at these, you're like, well, that's really far apart. Those are really far apart. So I expect this to be, the relative distance to be pretty big.
Oh, okay.
I expect that. Now, so that's the chi-square star, if you want to be insane. What's the critical chi-square? No, Jeff. What's our critical Luke Skywalker? What's our critical chi-square? What's in here?
11.345.
No. 0, 1. 0, 1, level of significance. What's the degrees of freedom? We already said it was 3. So if you look at the chi-square chart, where did I put my chi-square chart? Oh, I got so much shit up here. Okay. Degrees of freedom 3. 0.01 is over there. Jump it up. 11.345 would be enough evidence. And we got where? We got 106, so we're like, we're over here. Right? So did we make it far enough away? Yes, so what's that mean? What's what we just did? What's it all mean? Huh? We have totally found evidence. Did we make it in that rejection region? Oh, we're deep in there. So we have found evidence, what?
Living in a secluded area, doing a certain kind.
Yeah, that these people don't match. You can just look at the question. Yes. Does this group match the general pattern? No. These people in the secluded area don't match the general pattern of cholesterol levels. Again, what is it? What on this picture? Where does they exactly match what we expected? Where is that? At 0. So if we get at least this far away, that is evidence that it ain't the same, because this is where it's the same. This is like just because samples are different. You guys with me? Why is this okay? Because samples are going to be different. But then if I get a sample that is this different or more, holy shit. That is so unlikely that they probably aren't the same. There probably is something fundamentally different about these people. Then I can go in and do more deeper analysis. Is it their diet? Is there whatever? I can see what affects this the most. I could do correlation analysis, which would still be sort of a surface thing, but still. There's a certain fruit that grows there. If we crush the seeds up and make little pills, we can sell it to Americans. And in that form, it doesn't do shit for you, but we can say, hey, look, buy our shit, Americans. Okay. And we'll just eat it up. Alright. Okay. So, let me give you this here. I want you guys to try something on your own.